Okay, today we are going to try to finish the comparison sort techniques. So we've done the merge sort and the quick sort. Today we're going to do the select sort, the insert sort, and the heap sort. The first two are relatively straightforward, so I think we can move through them pretty quickly. The heap sort is a little involved, so we'll spend most of the time on that. So here in figure 4.18 we have the select sorter. All right, and there's this figure down below. Part B is the selection sort algorithm. Remember how it works? If you have the original list 7316284, then in the split what you do is you find the largest one and you put it last. And then you recursively sort, so it becomes, and that becomes 1, 2, 3, 4, 5, 6, 7, and then the join is automatic. All right? And now look, you guys, here is the only code we need to do, because the sort is the method that always gets called. Is all we have to implement is the split and the join. Now, do you remember the terminology here? The split and the join, are they the primitive methods or the template method? Do you remember? Okay, the split and the join are the primitive methods. The template method in the template method pattern is the method that executes the same for all. So that would be the sort. Are you with me? So remember, the template method pattern is one of the patterns in the Gang of Four, the design patterns Bible. And so all we have to do is the split and the join, because the sort has already been done for us. And furthermore, you can tell from the code, from this figure here, what's the code going to be for the join?
Nothing.
Nothing. Doesn't have to do anything. But the sort program will call the join and just return. Okay, so let's take a look. On this next slide, now we have the code for both the split and the join. All right? And in fact, if you take a look at the split, basically what are we doing? We're doing largest last. Right? In fact, I think I have a little, we can compare this with largest last, because what we do is we say int index of max gets low, for int I gets low plus 1, I less than or equal to high, I plus plus. And so if a sub index of max is less than a sub I, index of max gets I. Everybody can read this fine, right? And then at the end, outside the loop, temp gets a sub I gets a sub index of max, a sub index of max gets temp, and then mid gets high. Because we're setting mid. Remember, is mid called by reference or called by value in split?
Reference.
It's called by reference. So our job is to set it so that the join can use it. The other split can use it, and then the join can use it. But the join doesn't do anything anyway. So does everybody see? Everybody understands how this works. And look, here's the code for largest last. It's the exact same code. All right, so this is, I think we started the semester looking at statement execution counts and stuff like that with index of max. So it's just like that. And here in figure 3.1 is when we were analyzing this algorithm, it shows how it's basically the same code. So you see M gets, here in figure 3.1, M gets 0, but what M would get would be low, right? And then J goes up. And we compare, and if in part E we do M gets J because the 70 is greater than the 30, right? And so on, and then in the end we swap. So that's old news. But now, and so that's all the time we're going to spend on it, except for doing the performance. Now, you guys, can you tell us what is the recurrence for this? Here. It's split what? A, low, mid, high. A, low, mid, high. All right, so now let's do the big theta of each one of these. So let me think. How did we do the split? How did we do the split?
It's just largest last.
It's largest last.
For loop.
For loop. So what is good? So good observation. So therefore,
Big theta.
good. By Jove, I think we've got it. Big theta of n. And this sort was between, oh, and mid was way, mid is high at the end, right? Is everybody clear? Okay. So mid is high. So if we start between a low and mid minus 1, what is this? How long does it, if it takes t of n to sort n, then this is what? T of n minus 1. And what's this one? Between mid and high, that's just what? 1. Okay, so this is big theta of 1. And then what's this one? Big theta of 1.
And this is because, like, we know that the way that it's doing it is mid, quote, is actually only one number from the end.
Yes, that is exactly
And
right.
it's like-
That is exactly right. That's how we know that. We know that mid's going to be high. It's going to be over at the end. And it's only going to split off one element. So therefore, this is going to be Tn minus 1. So therefore, what's the recurrence? Yeah. So it's T of n equals, and the base case is what? Good question. Is it big theta of n or is it big theta of 1?
It's big theta of 1.
Oh, yeah. Oh, this is a really good question. I think maybe we were going to jump to some conclusions here. This is a good question. Is it big theta of n, or is the base case a big theta of n, or is it big theta of 1?
Base case is 1.
Base case is 1. Why is that? That's because this big theta of n is in the recursive call. Look, it's if low is less than high. Boom, 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 boom. But remember, but if low is less than high, so if low is greater than or equal to high, what happens? That's 1. That's the base case. So it's big theta of 1 if n is less than or equal to 1, and it's this t of n minus 1 plus big theta of this big theta of n. Now, is everybody clear on that? This was a good exercise. Does that look familiar?
It's clear.
Just a quick question.
Yeah.
We have 2 theta 1s. We only count for 1 because that's just the base case is going to be one of those 2.
No, 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 no. This theta of 1 has nothing to do with the base case. The base case is big theta of 1 because that's what happens if low is greater than or equal to high, and only that if statement executes. Are you with me? That was a good question.
Okay.
Are you with me? So basically what we have is inside the recurrence case, basically what we have is what? We have t of n, here, look, we have this. We have t of n minus 1 plus this big theta of n plus this big theta of 1 plus this big theta of 1. Now look how this works. But what does this mean? This means that it's some constant times n plus another constant, some coefficient times n plus another, and this means some constant, and this means some constant. So altogether, this is going to be what? Some coefficient times n plus some other constant. So this whole thing is just what? Is big theta of n. Now, do you see how that's the reasoning? I know this arithmetic is nebulous. But you think of this as being a function with some coefficients and some constants. You see what I'm saying? And here's some more constants, and here's some more. So this whole thing would be a. You see how they. You see this big theta of 1 is in here. Is in this big theta of n.
So then the base case is when the if statement is going to fail, and that just runs through once.
Yes. Yeah. The base case is if low is greater than or equal to high, because then there's no recursive call. Okay, now I ask the question again. Does this look familiar?
It's clear.
It is big theta. The solution is t of n is big theta of n squared, as you have seen recently. All right? In fact, somebody asked 1 or 2 classes ago when we were talking about this, how can we see that this is big theta of n squared? We can kind of see it because, see, each time you do t of n minus 1, that's one less, one less, one less. So that's going to get called n, it's going to be recursively called n times, but each time it's recursively called, there's a big theta of n that has to happen. So that's where the n squared behavior comes from. Can you kind of see that? All right. So that's the select sorter. Now, the insert sorter is your assignment for tomorrow, is it? I think you have a homework assignment due tomorrow. And it will be to complete the insert sorter, so we won't show you the code for this, but we can see what's going to happen with the insert sorter. So here, what happens is again, all we have to do is the split and the join. And how do you do the split? What's the split here? 7, 3, 1, 6, 2, 8, 5, 4. We just split up. We just do what? Yeah, it's just the last one. There's no computation. So the purpose of is in split is mid called by reference or called by value?
Called by-
It's called by reference. So is all it has to do is just set mid.
Well, how is this set different to the selection?
Oh, because in the selection sort, we did largest last. The one we just did, we had to go through in a loop and find the largest and put it last, and that happened in the split. But here, the split is simple.
Okay.
Yeah, you see the difference?
Mm-hmm.
So and then what happens is the split is easy, and then we recursively sort 7, 3, 1, 6, 2, 8, 5, and we get 1, 2, 3, 5, 6, 7, 8. And now why is this called insertion sort? Because now what do we have to do with join? We have to insert instead of selecting the largest and putting it last in the split, now we insert it into the into the sorted sublist. Does everybody see how that works? So we insert it in there, that's the code that you'll have. It's a very simple code. It's the code that, in fact, it's very much like the insert proceed. In fact, it is. It's the same thing as doing the insert in the. Do you remember when you did your vector p, vector t? I mean, basically it's the same thing. So this just a little. So here's in figure 4.19 is the code, and here I did the split for you. Mid gets high. And you can write a loop, just a little loop. And make sure to use your unit tests, okay, to test your code. So here's what happens. Suppose the initial list is 90, 20, 80, 50, 40, 10, 95, 60, 30, 70. And so, so low is the first one and high is the last one. And then when we do a split, in part B of the figure, mid gets high. So that was the code we just saw. And so now the 70 is just sitting there all by itself. And then we recursively sort A between low and mid minus 1. And so that gets us 10, 20, 30, 40, 50, 60, 80, 90, 95. And now we have to do the, and then it calls the sort for that one. It calls it, but it just returns because mid is not, because low is not less than high, so no work is done there, but anyway. And now we do the join. So now how do you do the join? So this join array A, low, mid, high. So what we do is we initialize J to mid and key to A sub mid. All right? Is everybody clear? So you have a little local variable called key, right? So and set key to A sub mid. So key will be 70. And now what do we do? Now notice that what we do is we start at the right-hand side and we go down, right? So we compare the 70 and the 95. And because 95 is greater than 70, boom, 95 goes in where the 70 was. And notice that we've wiped out the 70. That's why we have to put a little key value to store the 70. Are you with me? And then we compare the what?
70s.
Yeah, we compare the 70 with the 90. All right? Because the key, remember the key is 70, so we compare the 70 with the 90, and 90 is greater than or equal to 70, so we move the 90 over to where it belongs. And then we compare the 70 with the what?
80.
The 80, so the 80 goes over to where it was, is to where the 90 was. And then we compare the 70 with the 60, and what happens? Yeah, and so that's, boom, that's where it goes. All right? So you just code that up, a simple loop. Okay? Is everybody good? All right. Oh, rats. I erased the code. Okay, I'm just going to do, let's do split. Okay, so now for insert sorter, now what is the split? What's the big theta of the split? Big theta of 1. And then we sort, and what is this?
T and then
And what is this?
Oh,
T and then
yeah,
Minus 1.
I think this is T of n minus 1 is correct. And this one is what? Big theta of 1. And this join is what? This,
big theta n.
good, you got, good, we're getting good at this. Big theta of n. So what's the recurrence? Base case is what? Big theta of 1. And the recurrence, the recursive case is? T of n minus 1.
That's big theta.
Huh, does that look familiar? It's the same. And we already know what's the solution. By now we know what the solution of this one is, right? It's big theta of n squared. Okay? Is everybody? And see, you need to know each one of these individually. You need to be able to, I could ask you, individually. Say, what is the, and writing down the recurrence, well, anyway. But I think we're good on this. Okay, now here comes the complicated one. A little more complicated. Let's review what a heap is. What is a heap anyway? It's two things. It has to have two things. It has to have the what?
Heap order.
The max heap. Yeah, the first one. Let's do the first one. It has to have the max heap shape, which means what? If you go top down, left to right, there can be no gaps, right? So it has to have the max heap shape, and then it has to have the max heap order, right? And so the max heap order was what? Each node, the value of each node is what? Well, and for a max heap, the value of each of the root is what? Yeah, yes, greater than or equal to each one of its children. And then each child, and so on all the way down. So the left child also has to be a max heap, and the right child also has to be a max heap. Right? So here is a diagram from the earlier figure 4.5 of how the heap sort works. Now this is an interesting algorithm in that there is an initial build heap operation. So what we're going to see is in the code, this build heap is going to be in the constructor of the sorter. All right, and so what we're going to do is, because anytime you set up a sorter, this has to happen just once. This doesn't happen over and over and over again. What you do is you build a heap at the beginning. So in this figure 4.5, 7316284, if you write that out, if you draw that out as a binary tree with a heap shape, it will not have the heap order. So there is an initial operation called build heap that turns it into a true max heap with both the the max heap shape and the max heap order. And then what happens is, at that point, the split, because if if the root is bigger than each one of its subchildren, left child and right child, and each child is bigger than or equal to its subchildren and all the way down, that means, what do we know about the value of the tree at the root? It's the maximum of all of the whole thing. So once you know it's the maximum of the whole thing, you know where it belongs, right? So where does it belong? At the end. All right? So basically what we do is, the way we do the split is we take the first one, you see in this figure 4.5, 8, 6, 7, 4, 2, 1, 5, 3. You remember how it's stored in an array in order, right? So the first element is the maximum one. So what you do is you take the 8, and what do you think you do with the 8, you guys? You put it where the what is. In the diagram, the first diagram underneath build heap, it has 8, 6, 7, 4, 2, 1, 5, 3. We know 8 is the largest one, right? So where does it belong? It belongs where what is? It belongs where the 3 is. Are you with me? So what we do is we put the 8, we'll see this in a minute. What we do is, that's the way we split it. We split the 8 to where the 3 is. And then there's some adjustment. The way we do that to maintain that it's a heap. We keep it a heap all the way through. And so we heapify, and then we heapify the result. And then we recursively sort the 7, 6, 5, 4, 2, 1, 3, and we get 1, 2, 3, 4, 5, 6, 7, and then the join is nothing to do in the join.
So do you call the heap, like the build heap constructor, every time you do the sort on like the left-hand side to remake it into a heap?
That is a really good
Pull off
question.
the front and then make it a heap again?
Yeah, that is a really good question. The question is, so do we do build heap each time through, when we do the recursive call, the same way we did it at the beginning? And the answer is no. All right, we don't have to. So there's a way to get it, there's a way to do it without doing that, without reconstructing the whole heap. Yeah, that was a really good question, actually. And we'll see, that was a very insightful, and we'll see how it works. We're gonna investigate a specific method called Siftdown that's going to help us do these operations on this heap sort. So now, before we actually delve into the code, there are 3 relationships that we need to be able to compute. Now here in figure 4.23, we have a heap. So 95 is at the root, and let's see, is this a max heap actually? 95 is bigger than what? 90 and 80, and then 90 is bigger than 60, 50, 60 is bigger than 30, 40, 50 is bigger than 20, 80 is bigger than, yeah, this is a max heap, right? And let's suppose that this part of this max heap is stored in an array between 7, 8, low is 7 and high is 16. Are you with me? So low is 7 and high is 16. Now here's my question for you. My question, 3 questions actually. First question, if you need to find the index of the parent node, how do you calculate it? So let's just take a look at figure 4.23, and let's take a look at the 70. Now what is the index of the 70? It's 12. So here, let's do this. Index of 70 is 12, right? Now, what is the index of the parent of 70? The parent is 80, but what is the index of the parent?
9.
It's 9. Now, so the parent of the node at index 12 is what? Now, do you know what this is? This is a mathematical symbol for floor, and what does it mean? Round down. Okay. Now in C++, we don't need to bother with it, because in C++, if you divide by 2 and there's a fractional part, but you are dividing integers, what does it do? It drops it. So our C++ code does this for us automatically. But mathematically, if there was a 0.5 or like 3.5, this would be round down to 3. This is called floor. And there's another one called ceiling that does what, obviously?
Rounds up.
Rounds up.
So even if you have like 3.9, you still do 3?
Yes. Of course, it won't be that because we're dividing by 2.
Yeah, obviously.
But yeah, in general, that's what that's
mathematical symbol does
that
the same thing
as
as
rounding down. Yeah. Even if it was 3.99999999999,
so you
9.
from this one.
it would be 3. Okay, so now look, you guys. Now what is low here? In this example, what is low? Low is what? What is low here? 7. And what is high? 16. And what this is claiming is that the parent of the node at index I is at index I plus L minus 1 divided by 2, the floor of that. So the index of 70 is 12, right? So let's see. So if we do 12 plus what? What does it say?
7.
Plus 7 minus what? 1. And the whole thing, what?
Number 2.
Divided by 2. And we do the floor of that. What is this? 19. 18 divided by 2 is, oh, look at what this is. It's 9. And what is 9? Parent. So can you see that this works in general? So what's the parent of 10? So it'd be 10 plus 7 is what?
Dang, that's so weird.
And it works. And not only that, it works for a right child too. What about 11? What about 11? That's just one more than the 10. But if you minus 1 divide by 2 and take the floor of that, it'll still be 8. Does everybody see how that works? So that's how you calculate the. That's how you if you're at the index of a child, the way you calculate the index of the parent is just with this little computation. Yeah.
So do these formulas, were they just come up, do people just brilliant people just come up with them, or is there a way
Yeah.
to construct them?
Yeah, you just kind of come up with them. But I mean, look, it's kind of obvious, isn't it? Why do you have a divide by 2? You have to have a divide by 2 because what are you doing? You're going up one level, see? And it's a binary tree. So it's roughly half. I mean, it's easier to see if L is 0. Actually, this is a little more general. All right. Now the next question is, so that's the parent of the node at index I is at this index. Now what about going the other way around? If by going from the index of a child to the index of a parent, what if you want to go the other way? What do we have to do? We had to divide by 2. But what if you want to go from the index of a node to its left child? Instead of dividing by 2, what do? Yeah, multiply by 2, right? So what does it say? It says the left child of the node at index I is at index 2 plus I minus L plus 1. So let's do an example of that. The index of 90. What's the index of 90? It's 8. So what do we have? 2 times 8 minus what? 2 times 8 minus 7 plus 1. So what's that? 16 minus 7, 9 plus 1 is what? 10. So where's 90? Wait.
That's great.
Oh, we're going the left child. Right. Yeah. So yeah, the left child is 10. And therefore, oh, and by the way, I didn't bother to write this down, but what is the index of the right child? It's this what? Now think about it, you guys. How are these stored?
Plus. Is it just plus 2 instead of plus 1?
Which is it? Is it plus? Is it this one? Is it the index of the left child plus 1, or is it the index of the left child plus 2? That it is. The index of the right child is the index of the left child plus 1. Why is that? That's because they're stored how? Left to right, left to right. So, you know, if this is the left index of the left child, the index of the right child is one more. Is everybody clear on that? I didn't bother to write that down. Are we good? And now one more. We're going to use this one too. The largest index of a node with at least one child. Now, before we take a look at the formula, let's see what this means. The largest index of a node with at least one child. Now, can you tell me which node is the largest, has the largest index, but it has at least one child? Does 70 have any children?
No.
Does 40 have any children?
No.
Does 80 have any children?
Yeah.
But its index is what? 9. Is there one with a larger index that has at least one child?
11. Well, 15.
15 doesn't have any children.
15.
Oh, the 50. Right. At index 11. Yes, in fact, at index 11, that is the largest one with at least one child. I claim that this gives you that 11. So here, let's take a look. The index of 50, or let me say it like this. Let's rewrite this whole thing. So, index of largest, the largest index, not the index of the largest element, largest index of node with at least one child. So for example, how to use this formula is the largest index of the node with at least one child. We claim that it's the floor of L plus H minus 1 divided by 2. Right? So now what's our L here? So this is 7 plus what?
16.
Plus 16 minus 1 divided by 2, right? And that's the floor of that. So what's 7 plus 16?
23.
Minus 1 is, divided by 2 is, and the floor of that is 11. So sure enough, 11 is the index of the largest index of the node with at least one child. And so we're going to need that in one of our algorithms. So is everybody clear on where all this stuff comes from? Okay, so here we go. Now, you guys, we have a key method here that you are going to actually rewrite. I'm going to show you some code here, and you're going to, for the following assignment, you're actually going to modify this. So we need to understand how this code works. So check this out. The code is called Siftdown. Okay, that's the name of the code. It's the name of the method. So we're going to have a method called Siftdown. All right? And this method has a precondition that every node below I, so I is going to be a parameter that we give to Siftdown, and the precondition is that every node below I satisfies the max heap property, but the node at I does not necessarily. And the postcondition is that every node including I satisfies the max heap property. Now this is really important that we understand what the precondition and the postcondition is here. So let's take a look at this example. You see, we have a tree that has the root is 85, the left child is 30, and the right child is a bunch of other stuff. That's what these triangles represent on these tree diagrams. We'll do this frequently. Okay, so everybody understand that this triangle just represents another big tree with a root and a left and a right, and the whole thing is like is one big heap, you know. Is everybody? Yeah. So that's what that stands for. And so what we're saying is, and then I is going to be a parameter that gets passed to Siftdown. Now look, let's take a look. First of all, and before we look at the 30, let's look at the 90 on the left child. Is 90 bigger than 45 and 55? And is 45 bigger than 40 and 25? And is 55 bigger than 20 and 40? Yeah. So does everybody see that the left child is a max heap? And similarly, what about the right child? 80 is bigger than 75, 35, 75 is bigger than 15, 70, that's right, 35 is bigger than 25, 10. So the right child is also a heap. So does everybody see that every node below I is a max heap? But what about the node at I itself? It's not. That's the precondition. Does everybody see the setup? Yeah, question?
Does it have to be, does it have to not be the max heap property at I for this to be run?
In the precondition, the element at I is not, okay,
By definition, it cannot.
well, it may be, it coincidentally could be,
Okay.
but what we're saying is that the precondition assumes that in general, the root of the tree at I is not a max heap, but the only difference between it being a max heap or not is that its left subchild is a max heap and its right subchild is a max heap. But only at I. That's the only place where it differs. See, here's what's going to happen. What's going to happen is we're going to have a heap, and then we're going to
Make lots.
then we're going to take that thing off. Actually, you can tell what we're going to do. We're going to take that maximum off, and we're going to put something else in there. And now, if everything else was a heap to start with, and this is the only one that's wrong, we're going to sift it down to make it right. This is really clever. Okay? So does everybody see that in part A of the figure, 30 does not satisfy the max heap property, but its left child and its right child do. So how does this code work? Here's what it does. Well, here, let's go back. So what's wrong with the 30 and the 90? What's wrong with the 30? What do we compare? The 30, we have to compare the 30 with the what?
The 90.
The 90 and the 80. So of those three, which one belongs where the 30 is?
The 90.
The 90. So what do? We swap it. Now wait a minute. If we put that 90 there, is the right child of 90 now still a max heap?
Yeah.
Yeah, because we compared all three of them. So we're not ruining, do you see what we're saying? We're not ruining the max heap property of the right child. Does everybody see how that worked? Isn't this clever? And now what happens is we compare the 30 and the what?
45.
And the 45 and the 55. And is the 30 in the right? Now, but by the way, if the 30 is in the right spot partway down, we can just stop right there. Right? Because it was guaranteed that everyone below it was a max. Right? But what do we compare now? The 30 and the 45 and the 55. So now what happens?
30, that's all.
The 55 is the one that belongs, that needs to be, okay, so the 30, you see why it's called sift down? 30 is sifting down. So here, 30 goes to where this is. So now here's, and notice here's our I, goes along with it. And now what happens? The 30, the 20, the 40, and what goes up? The 40. Yeah? Does everybody see how that worked? And now I ask you, let's take a look at the code first. I was going to ask you what the performance was. We'll do that next slide. Okay, and so here's the code. So it's called Siftdown. Now let's remember what the parameters of Siftdown are. First of all, we have A, which is an abstract sequence, so that's the array. Are you with me? And then we have low, I, and high. So there's three integer parameters. Low, I, and high. And the idea is that I has to be in between them. Right? Because this is being stored in an array. Okay? And there's a low and a high that it does the boundaries of the array. So the precondition is that, now what's a max heap? The array, but not including I. Okay? It's the array, but not including I.
Is that a 1 or an L?
1, I plus 1. You see, it's I is going to be, I is at the way we're going to use it is the max is going to be I, so it's I and then so I plus 1. Okay, so it's a max heap, but not including I. And then the precondition is that low is less than or equal to I is less than or equal to high. And the postcondition is that it's a max not between A and I plus 1 dot dot high, but I dot, so it includes I. It was a little awkward. I mean, it's a little awkward notation there, but I mean, you know, it's in the code, so I don't know. So now look, you guys, int child gets, now does that look familiar? 2 times I minus L plus 1. So that is the index of which child? The left child of I. Are you with me? Look at this code walkthrough. If child is less than or equal to high, now how could it not be less than or equal to high? How could child, yeah, coming over here to figure 4.23. Suppose we are at index 12, which is where the 70 is, and we calculate the index of the left child. Well, what's it going to be? If we calculate the index of the left child, what would it be? It would be bigger than what? Than the 16. And it wouldn't have a left child. Do you see how that worked? So it says, so the code says, if child is less than or equal to high. Well, if that's false, what happens? There is no left child and we're at the bottom and we're done. There's nothing more to do because we're at the bottom. Are you with me? On the other hand, if child is less than or equal to high, that means there is a left child, right? There is a left child. Now check this next if statement out. These are sequential ifs. If child is strictly less than high. Now, if child is strictly less than high, what does that mean?
It's not high.
We're not at the end of the list.
Well, those things are correct, but that's not crucial. If child is strictly less than high, what is that telling us? There is a what?
There's a left child.
No, we already know there's a left child.
There's a right child.
There is a right child. Does everybody see this? If child is less than high, then there is a right child. Are you with me? Because,
It's minus 1.
yes, because, yeah. If child is less, if child is, because child is the left one, so if child is strictly less than high, then there's another one to its right. There's another one next to it, right? But now look, now what are we comparing? And a subchild is less than what? A subchild. So what are we comparing? The left child and the what? And the right child. Are you with me? Now wait a minute. What if there isn't a right child? What does this code do? Tell me a feature of C++ that happens that we're relying on here. What if there isn't a right child? What does this code do? Crash because it's outside the bounds of the array? Oh, did you guys not know about how if statements and loops work with binary, with and?
If one of them
Starts with an S? Oh my goodness.
Sequential?
No,
Segmentation fault.
no. Oh, these are all good. Segmentation fault, that was a good one.
Fails and like it stops.
No, it starts with an SH. Shh. Oh, come on. Oh, we need to know this. This comes up. Okay, what are the 3 goals of this course? Yeah. First one is data structures. The next one is object-oriented programming design, and then that is C++ coding. And this is C++ coding. You guys don't know this? Yeah, I'm sure you do. You'll say, "Oh, yeah, I knew that." Yeah, good. Oh, we need to review this, it looks like. You don't remember short circuit evaluation?
Rolls through it, like the moment the end fails, like then it starts, then it just.
It doesn't, yes. This code depends on short circuit evaluation. Now let's analyze this really carefully. It says if child is less than high, then what does it say?
And.
And. Now if child is less than high is false,
It doesn't do both of
it does not do a sub child is less than a sub child plus 1. It short circuits because it doesn't have to, because the first one is false. So if you put these in the opposite order, the code would fail. The code would be incorrect.
With like a segmentation rule?
Well, you could go outside the bounds of the array, no telling what would happen. Now, does everybody see what we just did? This should be reviewed. Yeah? Okay. So let's recap again. When we say int child gets 2 times I minus low plus 1, child is the index of the left child, right? If child is less than or equal to high, that means there is a left child. Otherwise, there is not a left child, and we're done. Okay? And then the if statement says, if child is less than high, that's saying that there is a what?
If there is a right child.
There is a right child. So if there is no right child, we don't do child plus plus. But if there is a right child, what do we do?
Then you compare it to the left.
A sub child is less than a sub child plus. So what is that comparing? The value of the left child and the right child. Are you with me? And if a sub child is less than a sub child plus 1, that means that means the right child is bigger. So what do you do with child? Child plus plus. So at the end of that if statement, child is the index of the larger of the 2 children. Now, do you see that? That is some slick code. Are you with me? And now what happens is, if a, now here we go, if a sub I is less than a sub child, then first of all, if a sub I is greater than or equal to a sub child, we're done. And there's nothing to do. But if we need to sift down, what happens is temp gets a sub I gets a sub child gets temp. So there's a switch. And what do we call?
Sit down.
Sift down, only this time between what? A, between low and high, stay the same, but now it's with it's child. Does everybody follow this? Yeah? So that's how we do. Look, so that's how each one of these operations works, see? 55. And it's recursive. It's recursive. And what your assignment is going to be for, when's homework due here? Tuesdays and Fridays? So what your problem for Friday is going to write this as a loop instead of recursively to optimize it. But this is the logic of it. Okay? Good deal. See you tomorrow. We'll analyze it. More heap sort tomorrow.